Hello students, this is lecture number 37 and we are going to start a new chapter. So, chapter number 10, this is the last chapter and this is about the beam. Okay. So well, beam you must have studied in solid mechanics, yeah, and here I am going to derive the beam equation which is known as Euler Bernoulli beam equation, and this you must have studied already during your solid mechanics classes, but still I am just going to derive to just to this will be just a revision first for most of the students. For those who have not studied solid mechanics, for them also they will know that from where the equation is coming, and that they will understand that. Yeah, so we could have started just from the equation as well, and it would have saved like 1-2 video lectures, but still I want to do this way, derive first, so that you understand what is the meaning of that equation. So beam, as you know, it means that there is a bar and which is loaded like this. So this is loaded perpendicular to the axis. This, if this is axis, this is loaded perpendicular to the axis. Then what happens? Because of that, this is going to bend something like this, yeah, or the beam could be something like this one, which is fixed at both the ends, and then you apply a load here, and then this is going to bend something like this. Yeah. So this is a beam, basically the has 2 degrees of freedom, as you can see, so this has 2 degrees of freedom, okay, 2 degrees of freedom, and that really means that at any points it has two things. One thing is how this is going down, how much is the displacement. So first is displacement, yeah, displacement, which is uy. So we are just concerned about how much it is going up and down only, okay. We are not concerned about how it is going this way, because there is no loading in axial direction in case of pure beams, and hence only u y will be there, and second thing will be the theta. Theta is how much this is making the angle. So it is possible that it has some displacement. So let us say displacement here, for example, could be the same. Let us say here and here is the same value, but there is a difference. Difference is here angle is like this, right? And here angle is like this. Yeah, so here if you say slope is 0 here, but slope is not 0 here, hence there is a difference between the two. So this theta is the slope basically, yeah, and this also which is equal to nothing but duy over dx. Yeah, so there are 2 degrees of freedom basically, although this is a dependent. So this will depend on ui, but still they are 2 degrees of freedom. Okay, so let's first derive it. Okay, so let's say there is a beam which is like this one. Okay, this is under load, and we look at, we just cut it from here and we will analyze that. But before that, we also say that there is a loading on the beam, which could be something like that. So let's say this loading is px, yeah. So our x direction is this way, yeah. So so on that there is a, on beam there is a load. So this is the meaning that beam could be something like this, see, like this, and it may be fixed like this one, and on top of that there is a distributed load over it, and because of that this is going to deflect like this, the beam. Okay, so let us say this one is the distributed load which is Px, yeah. So, we will write it, this is distributed load, yeah. Okay. Now, we will analyze that. So, we have what we have is we will take this. So, we have taken a section of this. So, this is what this one. Okay. So, this is the section, and on that we have the forces apply. The Px is there, distributed load. So, this is Px. So, Px will be the unit will be like a Newton per meter basically. So, this is distributed, yeah. Okay. And which all things will be there. So, this will also have some like shear forces and bending moments. So, so shear force, let us say shear force first. So, this is the force, yeah. So, this is shear force generally we write as V. So, let us write V, this will be V plus dV over dx time dx, this is how it is changing. Okay. Then it will also have a bending moment, say m, it is m here, it will be m plus del m over del x times dx. Okay. Okay, so this is a total force. We are assuming there is no force in axial direction because this is a pure bending. So, this is, we are saying this is pure bending, meaning that there is no axial loading, yeah. So, we will assume no axial loading. Okay. Okay. So, if that is the case, then what happens? Summation of all the forces in y direction has to be equal to 0, this equilibrium equation. And if you see based on this one, if you see we have let us say distance from here to here is dx. So, what do we get? We get like this, we have V plus del B over del x dx. So, this is force upward, then downward force is V. So, minus V, then upward force is this Px. So, plus Px times dx, yeah, and all will be equal to 0 because this is a static condition, yeah. So, and hence this is what we can find out. So, this and this will cancel out, yeah. So, what we get? We get simply like this, we get del V over del x, yeah. Simply we get this equal to minus Px, yeah. So, you see this cancels out, and then dx cancels out. So, we have like dV over dx plus dp dV over dx plus Px equal to 0, hence this equal to this. So, this is one equation we get out of it, yeah. Okay. Okay. So, let us say call equation 1. Now, next thing is this bending moment, right. So, we have this bending moment, and we can take like moment about a point, yeah. So, let us say we can take moment about this one, yeah. So, let us see how it works out, yeah. So, if you take moment about this one, then what happens? So, second condition will be summation of all moment is equal to 0, and hence we are going to take moment about which point? About this point, let us say. So, we have what? We have m which is anticlockwise, as a clockwise, then m plus dm over dx is anticlockwise. So, difference between these and 2 basically. So, what we get is m plus d del m over del x dx minus m. So, we wrote both of them. So, we wrote this one going this way, m plus del m over del x over dx goes this one minus m. So, this one. So, this is anticlockwise, okay. And then v, if you say v also have times dx. So, v is also anticlockwise. So, this m plus dm over dx is anticlockwise, v is also anticlockwise, right. Okay. So, we write here plus v times dx, okay. So, v times dx that we get. So, here this anticlockwise, this clockwise, so goes minus, and this is anticlockwise. So, that will be plus, and this will be minus p x multiplied by dx over 2, because of that will be clockwise. Yeah. So, plus p x dx times dx over 2, and all of them will be equal to 0. Okay. Now, what we see here is this and this getting cancelled out, yeah, and here we have dx multiplied by dx divided by 2. So, dx square. So, this is second order, right. So, what we will do is we will make this equal to 0, this and this cancels out, yeah, and what we get therefore is del m over del x plus v equal to 0, or simply v equal to minus del m over del x. So, this is what we got the second equation, like this one. So, first equation we get here, which is dv over dx equal to minus px, and here we get v equal to dm over dx. Now, we will combine them together. So, we have this equation, right, we have this equation, and then we have this equation, okay. So, from 1 and 2, so just write here from 1 and 2, and what do we get? So, take this dv over dx over this, and v is minus dm over dx. So, we are combining together. So, we will take the first equation. So, del, so what do we have? Del b over del x equal to minus px, and from v we put here, and then we get del over del x minus del m over del x, right, equal to minus px, or we get, so we put the value here, we put minus here. So, what do we get? We get minus del square m over del x square equal to minus px, or simply we get del square m over del x square equal to px. Yeah. So, this is another equation we get, or we can write or del square m over del x square minus px equal to 0. So, this is the equation that we get. Okay. So, this is the equation of equilibrium, and this is also the actually the root, this is also the strong form. Okay, but still we have to find out how m related to the displacement, because this is the just one equation that we get which has the forces in it only, the bending moment is there and the distributed load is there, but we want to find out how m has the displacement value in it. Okay, so that we have to still find out. So let's call this equation as equation number 3. Now we have to now see how this equation has the displacement term. Yeah, so for that we have to do some more analysis. Okay, so first let's understand what is the meaning of a strain. Yeah, so meaning of a strain in this case, and from there we will go. So they are all related. So this bending moment and a strain. Finally, we have to write bending moment in terms of a strain, then a strain in terms of displacement, and accordingly we can find out in this case. Okay, so let's start with the strain one. So let's see if you have a pure bending case. So pure bending will be something like this one. Yeah, so this is pure bending, and pure bending will be like a pure circular. So there will be, let us say this a small thing that we analyzed here, same one, yeah, same one, or even the whole of it also we can analyze, assuming that bending is very small. So very small theta. However, here we are just exaggerating that theta is very large like this one, but actually the theta will be very small, or the radius of curvature will be very large. So if this is the thing, so let's say we are measuring from what is called it neutral axis. So neutral axis means this is neutral axis. Okay, so neutral axis passes through the centroid basically in case of pure bending. So passing through the centroid. So basically you don't have to this is just not given. Basically we can find out a condition in which you will automatically see that this has to pass through the centroid, but I am just writing it here so that also you remember. Okay, so this is neutral axis where this passes through the centroid of the section. So let's say this section, if you take the section from here, so this will, it may look like this one, and this is the neutral axis. Yeah, this is the neutral axis, and here it is really the centroid here. Yeah, okay. So if this is theta, and let's say this is the rho is the rho is the rho is the radius of curvature. Okay, and from the section, let's say we take at certain point, this point, let's say at this point we want the strain, to calculate the strain, and this one, this y is basically measured from the centroid or from the neutral axis. Okay, and this y basically there we will find out if the radius of curvature till here is rho, then till here this will be rho minus y, simply, right? Okay, okay. So basically if you see, you can see that the outer fiber will have more tension than the inner fiber. Yeah, so since this is upward, right, upward, that means here this is a compression. So what we will see that there will be a compression here, and there will be tension here. Yeah, okay, and hence the strain in this case will be, so we can find out a strain, this equal to, this will be a strain in x direction, right? So in fact we can write epsilon xx equal to a strain in x direction will be equal to, where at this point will be change in length. So change in length divided by total length, right? So change in length is what? So, initially all of them would be like so neutral axis will have no deformation. Yeah, so you can neutral axis. So you can say no strain on neutral axis. So all this condition we will get later on, but just we are writing upfront so that we can also relate later on. So this strain will be delta L, means change in the length at this point. Yeah, at this point. So this point we can have the same point here, we can have here, right. So this is the point. So from here to here is y. Yeah, okay. So change in length over L. So original length is the length on the neutral axis, because neutral axis has no strain, meaning that there is no change in length, and that will be rho times theta, right. So this will be just rho times theta, and this delta L will be change in length. Change in length is what? So the original length is rho theta. So here we have, and the current length is what? Rho minus y multiplies theta. So we have rho minus y times theta. Yeah, okay. So what we get? We get simply equal to minus y over rho. Yeah, you can see that, right. So this rho theta cancels. So minus y theta over rho theta. So we get minus y over rho. So epsilon xx equal to minus y over rho. Okay, so this is what we get. Okay, so this is our equation, epsilon xx equal to minus y over rho, and let's call this equation number 4. So this is telling us how a strain is related to the radius of curvature and distance from the neutral axis, distance of the point of interest from the neutral axis. This is y, this is what. Okay, so again this is just the revision of the solid mechanics. We are trying to find out the equation itself. Okay, so yeah, so this is once we have that, the next thing is to we know a strain, we can find out if we know the radius of curvature and y, but again we have to find out what the rho is, because rho is not given, right. So y still know at the section. If you want the strain to be calculated here, so we know what is the distance from here, so that we know from here what is the distance, but what is the rho we don't know. So we have to find out the rho. How do you find out? So let's say you have x here, y here, and this is the beam, how it is going like this. Yeah, so we can see this is the initial point, this is the final point. Yeah, and this is from here to here, this is what the dx will be, and from here to here what is the dy. Yeah, and here to here is say ds. Okay, when this is very very small, dx, dy, ds very very small, then we know that we can write how they are related. They are related like this: ds square equal to dx square plus dy square, right. Yeah, or ds equal to root, right, dx square, or simply we can write like 1 root 1 plus dy over dx square times dx. This is how we can write. Yeah, okay. So this is how the ds is, ds equal to like this one. So basically ds is from here to here is written like this one. Okay, now what do we have to find out? We have to find out rho, remember. Okay, rho. And how do we find out rho? Rho, you can relate it here. So if you ds here, and let's say from here we are drawing a perpendicular line from here, and from here also we are drawing perpendicular line, and wherever that meets, yeah, so this is what the rho will be, right? From here to here, rho, this is going to be rho basically. Yeah, so and what is the relation? Relation will be rho, or and if let us say from here to here, this is d theta. Yeah, so relation will be rho equal to ds over d theta. That's what it is going to be. Okay, so ds we have found out from here. Now d theta we have to find. D theta, how do you find? So if you see here, d theta will find out from here. So if we have, so d theta is nothing but the d theta will be also equal to, so let's draw one more thing. So if say this is the tangent here, this is the tangent here, so this angle, let us say this angle is this angle is say theta 1, this angle is theta 2. Yeah, okay. So d theta is nothing, so d theta will be equal to theta 2 minus theta 1. It will be equal to like that. Why? You can see that, like you have 90 degree from here to here, right? So see here, this is theta 2, this is 90 degree, this is theta 2, this is from here to 90 degree. So the angle between the two will be simply this minus this only. Yeah, so here so we can also draw like this one, right? From here, if we draw parallel to this one, then from here we can measure. If you see the, so let's do it. So the first one, say we are talking about this. So let's say at this point we have 90 degree like this one, and yeah, and from here we have theta 2, there is another point here, let us say, and here this is 90 degree and this is theta 1. So we have to find out the relationship. So here, so we are measuring from here. So this is theta, this is theta 2, this is 90 degree. Yeah, so what is the value here? So here it will be, so this is theta 2, so this angle and this angle will be the same. Okay, what I mean to say is this is and this will be the same, and what is the value? This will be 90 minus theta 2, so hence this will be also 90 minus, or pi over 2 minus theta 2. Yeah, okay. Similarly here, if this is like this one, then here, so this will be pi over 2 minus theta 1, right? And from here to here, this will be pi over 2 minus theta 1. Okay, so this angle, will be what? This angle will be this one, this is a big one minus the small one, right? This will be what the angle will be. Yeah, so basically what we will get is equal to pi over 2 minus theta 1 minus pi over 2 minus theta 2, which is equal to theta 2 minus theta 1. Yeah, okay. Okay, so what we get, d theta equal to theta 2 minus theta 1, but theta is it is the slope basically, right? Theta 2 is also, which is, since theta 1 theta 2 is very very small, so we can also write will be equal to what? So we can have now like this. So let's say at this point, let's call a point A and this point B. Point A we have the slope which is dy over dx, and the point B, so this is A, point B you have du over dx, right. So du over dx, then plus du over dx, d square you dx square times dx. Yeah, so this is varying, so we can write it like this one. Okay, and so hence we get this is theta 2, this is theta 1, theta 1 is equal to like this one, this will be the theta 2 value which is like equal to like this, the whole thing is theta 2. Hence we get this one is equal to this minus this, and hence we get this is nothing but d square d square y over dx square, yeah, times dx. Yeah, so that's what we will get. This value will be something like this only. Okay, so one thing guys, here I have used partial differential, but actually there is no other like coordinate system here, only x here. Yeah, so you can take this as the total differential rather than just partial. Okay, so yes, although I have used the partial, but there is no other coordinate, so we can also take it as the total differentiation. Okay, so here I have used total only for that purpose only. So, okay, so if we have that, then rho becomes what? Rho is equal to ds, which is this equal to divided by d theta, and d theta is equal to like this one, right? So we get rho equal to ds over d theta, and ds equal to 1 plus dy over dx square and dx divided by d square y dx square dx. Yeah, so this and this will cancel out, so this we know that we know this is how the rho is from the calculus. It's from the plus 2 level, plus 1 plus 2 level from your high school, you know this also. So actually we did not have to explain this way, but still I did, so that you have no confusion. So this is a rho here which is given like this one. Now we are assume dy over d theta, dy over dx, that is this is the slope equal to very small. So if that is the case, then this square term will go. Yeah, so what we will go get simply then rho equal to simply 1 over d square y over dx square, simply nothing else. Yeah, okay, or 1 over rho is equal to d square y over dx square simply. Yeah, right. So now, so a strain we can find out. A strain equal to, as we know, minus y over rho we found out. So this will be equal to minus y multiplied by d square y over dx square. Yeah, so this is the one equation. So let's call it equation number 4. Yeah, so we had third, this is 4 already, this is 4. So equation number 5. Okay, so we got this one, and this is going to help us. Yeah, so we know the definition of a strain now. So this is the strain at any point on the beam. Yeah, we can find out what we have to find out, del square y over del x square. Here y, remember that. Okay, one thing you have to remember, when we said y, what was the y? Y was basically how this is how this was moving. So basically for us y was nothing but, so okay, so let's see here, this curve moving like this one, based on that we derived. But for us this movement of y, this y is nothing but uy. Yeah, so equal to displacement only. It was a displacement only. Okay, so y variation here is because of displacement only, otherwise though no variation. So displacement y equal to uy only, and hence we can write this one will be the, okay, so okay, there is another confusion that this is this y and this y are different. Okay, so remember here this y, this tells you how much, what is the distance from the neutral axis. This y is basically is the uy. Okay, so maybe I correct here only, so this is uy. Let's call this one is nothing but duy. Okay, or maybe I leave it like this one. I will this is as per calculus. In calculus you called it dy and x, so as per the calculus, but here I will just make a note that y is equal to uy only. Okay, so uy equal to y. Yeah, so this is important here to note. Yeah, okay, so this y is different y, so this is different y, and this one is uy, basically this one from neutral axis. Okay, so our equation will be epsilon xx equal to minus y d square uy over dx square. Okay, so we write like this. Yeah, so this is equation number 6. Yeah, so strain equal to minus y d square uy over dx square. Why? Because our y, in this derivation, whatever y we have starting from here is equal to uy only. Yeah, so hence we have replaced that with uy. This y remains the same. This one is the distance from the neutral axis. Yeah, so distance from the neutral axis. Now that we know the strain, we can find out the stress now. So sigma xx will be equal to Young's modulus multiplied by the strain, and which will make minus E y d square u y over dx square. So this is the stress. Yeah, okay. So basically when you have to find out the stress, you can use this formula to use it to find out the stress. Now the still we are not able to relate it with the original equation. So the original the strong form was like this one, right? So d square m over dx square minus px. We have not related, we have not got m basically, so we have to find out m. So although we got some equation like a stress, we found out like this one. So far we know the stress is equal to this one, which is equal to minus E y multiply this one, which also comes from, we can also write E y over rho. So this was it was earlier, and rho we found out to be, so this is equal to minus y over rho, and multiplied by E you get the sigma. So we have this, which is equal to this one, we know this one. Now what you have to do, find out m. Okay, if this is like this one, then m equal to what? So we know here now that the sigma is a so sigma has these values of d square uy over dx square. So that means displacement term it has. If we can somehow find out m, then that m in terms of this we can put in the strong form, right, and then we will get the whole equation. So we want to find out m. So what is that? Okay, so now let us say there is just this is a section we are talking about, right? So on the this is a section of the beam, and there will be some stresses there, right? So the beam is being bent like this one, and we are talking about once a small slice of length this one, and the slice here, the section, if you see the section here, which will look like this. So this is the section, right? So it will have some, you know, some width, say b, there will be some length, height, which will equal to h, like this one, right? And then there will be a neutral axis. Yeah, neutral axis goes like this at the section. This is the cross section, basically cross section of beam. So beam cross section, yeah, okay. And then we if we look at this, if it is bent like this one, then what happens? The top fiber, the top fiber will be under compression. So this will be compression, and this will be under tension, meaning that there will be compression here. So compression here and tension here. So we can also write this way. So we can show it like this. So this is a compression. So this is the how it is going to be. So the compression and tension. Yeah. So it is something like this. Yeah. So yeah. So compression here, the yeah. So that means this is a compression here, tension here, but this is the maximum compression here, means stress will be the highest, and then here the tension will be the highest there. So they will the value will be like this. Why? Because strain is minus y, right, over rho. So the highest y will have highest strain, yeah, and so on, right. Okay, so at a section the forces are perpendicular to this section here, because this is the we have cut like this one. So perpendicular to this are the stress here, right. So total force on the section, right. So we can write total force on the section, okay, F will be equal to sigma xx times d area, right, for the whole area. So this is the area of correct section is A. So this is that will be equal to E epsilon xx over A dA equal to integration, then we have minus E y over rho, right, dA. Yeah, we assume rho to be constant, basically the rho, which is the radius of curvature, we assuming this is very thin basically. So the rho becomes is the same for all the sections everywhere. Okay, so what we get is equal to minus E over rho and y dA, right, and total force has to be 0. So this will be equal to 0. Yeah, so because there is no axial there is no axial load. Yeah, so no axial loading, since there is no axial loading. Yeah. Okay, so if this is equal to 0, that really means that y dA equal to 0 means, so this also tells like the area, the moment of area. This is nothing but total moment of area, right? Total moment of an area equal to 0. That really means y is measured with respect to the centroid. So this only possible when y is measured from the centroid, that is y equal to 0 passes through the centroid. So then only that condition is true. So you know the y equal to 0 passes through the centroid, or y equal to 0 is the also neutral axis. Okay. Now this is what the we get from that. Now second thing, we have to find out m. Okay, so that we put that value there, right? So the m value, m equal to what? So this is bent like this one, you know, and this is here, this is compressive stress, means minus strain, this is plus strain. So m, if you see at the section, we have like this. So we have the negative stress here, positive stress here. So m will be equal to nothing but sigma, right? Sigma xx, right? Multiplied by dA. Okay, so multiplied by dA, so that makes it a force. Yeah. So let's say we are talking about at this point, the sigma xx multiplied by dA is the force at that section. So let's say this is the section, this is the neutral axis, we are talking about at this point here. So sigma xx is whatever the sigma is here, dA means whatever the small area, it is this one, multiplied by, so this is y here. Yeah. So that means from here to here y. So if we multiplied by y here, then what happens? Sigma yy is negative here, and then y is positive. So everything will be negative, but our convention is bending moment will have compression here, positive bending moment have compression here and tension here. So that means we have to multiply it by minus 1, so that we have the positive m coming in this situation. That means when we have outer fiber negate the compression, the lower fiber tension, with positive bending moment, if we want to enforce that condition, then we have to have minus here, that's why I wrote minus here. Okay, so that is equal to minus a sigma yy, nothing but minus E y over rho y dA. What we get? We get E over rho, and then we get this value. We get y square dA, okay, which is equal to EI over rho. What is I? I is the, so where I is equal to area and then y square dA. This is second moment of area, also known as moment of inertia. Okay, so moment of inertia, this is not mass moment of inertia, this is moment of area moment of inertia. So you can also write area moment of inertia. Okay, so that means what we get? We get m equal to what we got? ei over rho simply. So ei over rho. Yeah. Okay. Only thing remaining now is the value of rho. Yeah, so if you see here what the value of rho, we can put it there, we can find out. So get the value of rho. So what is rho here? So if you see here, rho is equal to 1 over rho is this d square y over dx square. So we can put it there. Yeah, so okay, so will be equal to ei times d square uy over dx square. Yeah, since you can write here, since 1 over rho is equal to d square uy over dx square, and hence we wrote like this one, or we got this equation m equal to ei d square uy over dx square. So say equation number 7, I don't know whether 7 is there. Yeah, 6 is there, no 7. So let's write equation number 7 will be like this one. Okay, so this is the equation we have, and the original equation was del square the original strong form. What was that? This was d square m over dx square minus px equal to 0, right? Okay, now and we get m in terms of uy now. So this thing we can put straight away here, and we can see. So what we get? We get d4 or d square over dx square, then ei d square uy over dx square minus px equal to 0. So we can see here, so this whole thing we put it here, yeah, and we get this. So this is the final strong form. Okay, of course there will be a boundary condition with that, and what will be boundary condition? There will be boundary condition like if this is a beam, right? So there will be there are two boundaries, a boundary 1, the boundary 2, and you will have what you see here is basically the fourth order differential equation, and hence you should have 4 things given at the boundaries, and each node has 2 degree of freedom. So you have to give, like there are 2 kinds of boundary will be gamma u boundary and gamma theta boundary. So so basically this one, for example, it will have gamma u1 boundary, you can say gamma theta 1 boundary, here it will be gamma u2 boundary and gamma theta 2 boundary. So accordingly we have to give these things has to be given. Yeah, so either we have to give a force here, some kind of force, so either moments will be known here or the displacement will be known. So there will be either, so you have essential boundary conditions essential boundary condition or natural. And what is meaning that say here gamma u1 for example. So it may be given uy given, maybe given or what is given, force. Yeah, so force y is given, right? It could be like this one, or gamma theta 1, let's call it. So theta is given, meaning that duy over dx is given, or moment is given, or m is given. M is given means there may be a bending moment given here. Yeah, so bending moment is given. Accordingly, here also will be either you have uy given here, or force is given. Yeah, so either displacement is given or the force is given. The other option is either the moment is given here or the slope is given. Yeah, so this is how the boundary condition will be given depending on the condition. Okay, you have to solve this problem, but this is how what the strong form is. This is how we have derived it, and next thing will be to derive the weak form basically. Yeah, so we have to derive the weak form. So we can formally write which all kinds of boundary condition is possible. So you have uy, so boundary condition will be on, boundary condition on. So uy will be there, theta which will equal to duy over dx. Then you will have on m, right? So m equal to equal to ei d square uy over dx square. So you will have on this one, okay, and then you can also have on the force. Which force? The shear force. Yeah, so on shear force v is equal to, we know that this is minus dm over dx, that we have derived already. So that makes it minus d over dx ei d square uy over dx square. So on the four things we will have the boundary condition. Yeah, so this and this will be natural boundary condition, and this and this will be this and this will be essential boundary condition, and this will be natural boundary condition. So this is we can identify here. So this natural boundary condition, yeah, and this one, these two will be essential boundary condition. Okay, where we know what that means. This is the deflection, call it deflection, right? Theta equal to slope, m bending moment, and v is the shear force. And these are the relation with the u, basically uy, the deflection or displacement. Yeah, so deflection, you also call it displacement. Yeah. Okay, so that means we have the complete picture now. So we have to solve this problem which has the deflection here. This is Young's modulus, yeah, and this is the the moment of inertia, area moment of inertia. This is the force, distributed force, this is the equation, and we have a different boundary condition. We have boundary condition directly on the deflection, it could be on slope, which is d uy over dx, or could be on bending moment. So m equal to ei d square u y over dx square, or on shear force, which will be v equal to minus dm over dx, which is like this one. Okay, so we have the complete picture now. The next thing will be to just solve the strong form. Basically, we have to first convert that into the weak form and then solve it. Okay, so that is all for this lecture.